So welcome everyone. I want to first of all thank the organizers for giving us the opportunity to present our results on high repetition rate, high harmonic generation with ultra-high photon flux, which is a work that has been carried out at Active Fiber Systems in Jena, Germany, together with different institutions in Jena as well as in Delft in the Netherlands. So first of all, I would like to briefly say a few words on Active Fiber Systems itself. So we are a company which offers different types of laser systems at 1 micron wavelength with different power levels, but also at 2 micron wavelength. We offer OPAs, other add-ons such as fuse cycle outputs with CEP stability. And what I would like to focus on today is how we combine our ultra-stable ytterbium 1 micron platform with a high-power XUV beamline. So as I said, the generation of XUV can be done with our ytterbium fiber lasers, and here are some exemplary configurations, but we are able to configure the source to your needs. So if you are interested, please visit our website or contact us directly. So motivation for this work is the process of harmonic generation itself. I would like to repeat briefly how this process is happening. So you have an ultra-short laser pulse which you focus into a gas target with intensities on the order of 10 to the 14 watt per square centimeter, and through nonlinear interaction in this gas medium you generate ultra-short and ultra-short wavelength radiation with tabletop laser systems. So that's why this process is so attracting, and because it's coupled to the laser field, it's also coherent, so that is, you generate laser-like radiation in these extreme ultraviolet or even in the soft X-ray region. And what's additionally important is that the pulse durations of this radiation can be in the femtosecond range or even the attosecond pulse durations. So for that reason, this process or these sources have found different applications, which can be found in surface science, atomic and molecular physics, spectroscopy, or imaging techniques. To be a bit more specific on the application part, for example, coherent diffractive imaging is one very prominent application of this radiation source, where you make use of the spatial coherence. So some very promising results have been obtained in different groups around the world. Other application examples are based on coincidence experiments, where you have to have a good statistic for your experiments. And finally, time-resolved photoemission experiments have been done in various groups with HHG sources. So depending on these applications, there are certain requirements that your source have to fulfill to be able to be used in these applications. And this differs from the application type. For example, if you use photoelectrons, then space charging become an issue. So that means you have to reduce the numbers of XUV photons per shot, per pulse. And at the same time, of course, you want to increase the repetition rate to ideally the megahertz regime to maintain a good signal-to-noise ratio. A similar demand is given by coincident applications. So I briefly mentioned that these sort of applications depend on a statistic where you have less than one event per laser pulse. And then, of course, to have a good statistic, you need to have as much signals, as much laser pulses as possible, and therefore also a high repetition rate XUV source would be beneficial. And generally one can say that all applications suffering from long integration times or low signal-to-noise ratios have to have a source with the highest possible photon flux. So that means we want to build a high repetition rate and high photon flux XUV source, and still to date most of these sources are based on Ti-Sapphire technology, which is limited to the kilohertz regime. And in the recent years, ytterbium-based laser systems have shown that they can operate in the megahertz regime, but compared to Ti-Sap, the pulse energy is typically a bit lower. So of course the question is how the efficiency of the HHG process behaves when you use these ytterbium laser systems. And to answer these questions, you basically have to consider one very important aspect of every nonlinear process, which is phase matching. It's shown very schematically here, involving the most important terms that play a role for harmonic generation. And as you see, you have a positive term, which is due to dispersion of atoms and the free electrons that are generated during the ionization process, and a negative term, which is due to the focusing of the laser pulse into this gas jet. And the important thing to notice here is that this first term is dependent on the density or the pressure of your gas medium to be tuned. And the other important factor is here this ratio of the actual ionization over a so-called critical ionization, which depends on the gas you're using. And as you can see here, as long as your actual ionization fraction stays below this critical ionization, then you can balance these focusing terms by tuning the gas pressure, so that you can achieve pressure-tuned phase matching. So without further notice, it has been shown in different works over the last years that the efficiency of this process is actually independent of the focusing conditions, and you also have to use ultra-short laser pulses to drive this process efficiently. So that means phase-matched HHG is possible with fiber lasers, and tight focusing has no effect on the efficiency, and eventually you need a high average power ultra-short pulse laser to drive this process. So, and of course, we were investigating how we can achieve that. So as I said already, ytterbium-doped fiber lasers have shown impressive power level over the recent years, but they suffer from pulse duration which are in the range of 300 femtosecond, which we have just learned is too long for harmonic generation. And one way to reduce the pulse duration is to use nonlinear compression in noble gas-filled hollow core fibers, as schematically shown here, to achieve 30 femtosecond or even sub 30 femtosecond pulses with up to 400 watt of average power. And recently a new approach based on multipass cells has shown even power levels into the kilowatt regime. So the advantage of this technique is that it's very flexible regarding your possible pulse parameters you can use, and that it is average power scalable and even can be extended to a second compression stage in which you can go down from this 30 femtosecond pulses to actually sub 2 cycle pulses or 2 cycle pulses range with power levels of more than 200 watt or even 300 watt with slightly longer pulse durations but higher energy. So the results I'm going to present in the next slides is based on our ytterbium 100 ultrafast fiber laser. Without further details, it is a 100 watt average power ytterbium-based laser system with 250 femtosecond pulses, and as shown here on the right side in the power and pointing graphs with excellent stability values. So we employ this source, so this ytterbium 100 watt laser is shown here, to drive a nonlinear compression stage, which output has more than 60 watt, less than 40 femtosecond, and in this case operated at 500 kilohertz. So the pulse energy is a bit more than 120 microjoule at the central wavelength of 1030 nanometer. And due to the use of this very stable source, also the nonlinear compression source operates in a very stable manner. So here shown a measurement over 15 hours with average power stability of about 0.1% RMS. So as shown here, the output of this nonlinear compression stage, so this 40 femtosecond, 60 watt or more than 60 watt pulses, are then focused into a gas jet here. They travel into a second chamber where the laser is separated from the XUV, and then the XUV output port is sent into the actual experiment. So in this particular source has been optimized for two different wavelength ranges. One is the 70 eV photon energy range, which is shown on the left side here, and then a second optimization point is around 100 electron volts, also including the important 93 electron volts for semiconductor industry, but it goes all the way almost or above 150 electron volts. And what is remarkable is that due to the high average power driving laser, we can actually in most of these spectral ranges achieve photon fluxes that are at some points above 10 to the 11 or above 10 to the 10 for this high photon energies, photons per second in a 1% bandwidth, and actually some of these values are world record fluxes that have been achieved to date. To put this a bit more in perspective, here is a graph showing the a summary of different HHG sources, plotted average power over photon energy for different laser systems. And as I said, the source I have just presented here actually is located in this region and in this region. So these are the two optimization points I have mentioned. And as you can see, in both of these regions, we can achieve the highest photon flux demonstrated to date. So generally one can say that fiber lasers now drive many of the high flux tabletop coherent XUV sources, and therefore they will find their way into different applications in the future. So in addition to these remarkable parameters, we can also offer an excellent long-term stability of the source, which is shown here on the left. So this is actually the XUV beamline right before shipment to TU Delft, where it is used within the LINX project, where partners such as ASML investigate different imaging techniques. And we have also seen that the average power stability, here in this case, this is the 70 eV photon range, and in this case the 90 eV photon range. And as shown on the right side, the stability is just around 1% RMS for each of the individual harmonics. So as I said, this source is being implemented in this LINX project, and here's a short movie that has been done by TU Delft, which actually shows the application that is planned for the source. Here's our source, and then the XUV is sent into the target chamber of the customer, and they are using different imaging techniques to push resolution and find new ways for semiconductor industry to image their chips. Okay, so if you are interested in further details on our products, or even have a bit of a glimpse on how we work, I can highly recommend to visit our virtual lab tour, which we have recently launched, where you can visit different laser systems, such as this one, the HR laser for Eli Alps, and different other laser systems in our labs. So in summary, I have shown that we have constructed a source, HHG source with very flexible parameters in a compact design. We can offer a record high photon flux at 18 nanometer and between 10 and 12.4 nanometer. And to put this into numbers, at 18 nanometer we can generate more than 3 times 10 to the 11 photons per second, all values given in a 1% bandwidth. At 12.4 nanometer, still more than 3 times 10 to the 9, and at 10 nanometer the flux is still above 10 to the 10 photons per second. And with that, I would like to thank you very much for your attention.